Dear students, probably from my earlier videos, you are getting some ideas on spectroscopy basic and nuclear magnetic resonance spectroscopy. In this video, we are going to discuss electronic spectroscopy, which include number 1, what is electronic spectroscopy, number 2, types of electronic transitions, number 3, chromophore and auxochrome, number 4, Beer-Lambert Law, number 5, absorption and intensity shift, number 6, effect of solvent polarity, number 7, Woodward-Fisher rules for calculation of absorption maximum in conjugated diene carbonyl compounds. So there are some rules which determine the absorption maximum. So let's start with what is electronic spectroscopy. So electronic spectroscopy is nothing but UV visible spectroscopy, which energy wavelength range is 180 to 400 micrometer. So another name of electronic spectroscopy is UV visible spectroscopy because the absorption of UV visible radiation by a molecule leads to the transition among the electronic energy levels of the molecules. So if we see the theory of electronic spectroscopy, normally the peaks are observed in very broad. Why? Because as we see the potential energy diagram, the potential energy is plotted against internuclear distance. So these are two, E1 and E2 are two electronic energy levels. So excitation of the electrons will occur from E1 to E2. Now we will see that each of the electronic energy levels include numbers of vibrational energy levels V1, V2, V3 and rotational energy levels R1, R2, R3. Similarly in E2 also vibrational energy levels and rotational energy levels. Thus there will be large number of possible transitions responsible for change of rotational, vibrational and electronic levels. Hence, large numbers of close wavelengths absorbed resulting from the formation of the band, and hence the peak which is resulted during electronic transition is very broad, not a sharp line, because it involves numbers of rotational and vibrational energy levels. Now one more thing is there, that is one principle, that is Frank-Condon principle, which implies that during the electronic transition the internuclear distance change is very negligible. So from A1 to E2 transition the internuclear distance can be negligible, and this is Frank-Condon principle. Now let's discuss what are the types of electronic transitions. So according to molecular orbital theory, when a molecule is excited by absorbing UV visible rays, energy from UV visible rays, then the electrons is promoted from bonding to the anti-bonding orbitals. So there are four types of transition. One is sigma bonding to sigma anti-bonding, non-bonding to sigma anti-bonding, pi to pi anti-bonding, non-bonding to pi anti-bonding. And here the sigma bond is very strong bond. So energy required to break that bond, the electronic transition, is very high. So order of energy is sigma star is greater than n sigma star, then pi star, then n pi star. And since energy and wavelength are reciprocal to each other, so order of wavelength will be in the reverse order, that is n pi star has the longer wavelength. So first one is what is sigma star transition. The sigma star transition will be occur in case of saturated system which has only sigma bond. For example, methane, propane are absorbing at the wavelength of 150 micrometer. Normally this transition is occur in vacuum system because in that wavelength 50 micrometer the oxygen present in air will strongly absorb. So this sigma star transition is performed in vacuum medium. Next is n sigma star transition. So in n sigma star transition, the molecule should have a lone pair of electron. That means it should be attached to the atom which has lone pair of electron. For example, methanol absorbs at 174 micrometer, methyl chloride absorbs at 172 to 175 micrometer, methyl iodide absorbs at 258 micrometer. If we see methyl iodide and methyl chloride, the energy required, this is wavelength, so energy required for methyl iodide is less compared to methyl chloride, because in methyl iodide the electrons are loosely bound. Similarly, if we see pi-pi star transition will occur for the unsaturated system which have pi bond. So unconjugated alkene absorbed at 170 to 190 micrometer and carbonyl absorbed at 180 micrometer. Similarly, non-bonding to anti-bonding pi star transitions, this will be occur where the molecule has lone pair of electron as well as it has unsaturation. So carbonyl compounds show both type of transition, pi star and n pi star at 180 micrometer and 290 micrometer. So these are the energy ranges. This is sigma, pi, non-bonding, then pi star, sigma star, sigma star, n sigma star, pi star, n pi star. So energy range is sigma star is greater than n sigma star, then pi star, and n pi star. Next, we need to learn what is chromophore and auxochrome. So chromophore is the any atom or any molecule that imparts color to the compound. So these are the example which impart color to the compound: alkene, alkyne, carbonyl, nitro group, cyanide group, conjugated diene, benzene, alkyne, conjugated carbonyl, etc. And auxochrome is which is not itself chromophore, but the presence of this molecule will enhance the color imparting property of the chromophore. So for example, aniline. Suppose benzene is chromophore and is absorbed at 255 micrometer, but aniline, when in presence of NH2, it will absorb at 280 micrometer with increased intensity. So presence of aniline is enhance the color imparting property. Next is the Beer-Lambert law. Already it is discussed, but still, without Beer-Lambert law, the discussion of electromagnetic spectroscopy is not completed, because this law covers the absorption of light by a molecule. So absorbance A is equal to log of I naught by I is equal to epsilon CL. So I naught is the intensity of the incident radiation and I is the intensity of the transmitted radiation. So A is directly proportional to the concentration of the sample, which is in mole per liter, and thickness of the solution which is taken in L in centimeter. So epsilon is the molar absorptivity or molar extinction coefficient, and in organic compound, which is where electronic spectroscopy is measured, the absorption spectra is plotted against epsilon, this epsilon, and wavelength. So absorption maxima is plotted in y-axis epsilon and x-axis wavelength. So we will get a plot like this. Now if this lambda max, this is lambda max, this is absorption maxima, epsilon maxima. So if this wavelength is shifted to longer wavelength, this right hand side, then it will be pethochromic shift, and if it is shifted to shorter wavelength, left hand side, this is hypsochromic. If the epsilon maxima is increased, it is hyperchromic shift. If the epsilon maximum is decreased, then it is hypochromic shift. So pethochromic shift is red shift shifted towards longer wavelength, which is occurred when conjugation in the alkene is increased. And hypsochromic shift is the absorption maximum shifted to shorter wavelength, and it is observed when it is called blue shift. It is observed when conjugation is removed. Suppose for this example, lambda is 280 micrometer when it is conjugation, when it is in conjugation, but in presence of proton the conjugation is removed, then lambda max is shifted to shorter wavelength. And hyperchromic shift, intensity is increased, and hypsochromic shift, intensity is decreased. So hyperchromic shift is observed when we are adding some oxochrome in the molecule, and hypsochromic shift is occur when the symmetry of the molecule is distorted. So these are written here. Next is effect of solvent polarity. So now what will happen if the spectrum is recorded in non-polar solvent and if the spectrum is recorded in polar solvent? So normally in alpha beta unsaturated ketone, it is observed that in alpha beta unsaturated ketone we have pi star transition and n pi star transition. So when shifting from non-polar to polar solvent, normally polar solvents are protic solvent which have hydrogen bondings. So when pi star and n pi star transition, if we see, then shifting from non-polar to polar solvent, the non-bonding energy level is quite stabilized, and pi star energy level is also stabilized compared to pi, because the non-bonding energy level is stabilized due to the hydrogen bonding with the polar solvent, and pi star orbital is stabilized because pi star orbital is more polar compared to pi. So it is stabilized. So as we see, when shifting from non-polar to polar solvent, pi star transition, the energy for pi star becoming, it is less. This is C is less than A, and n pi star transition is becoming more. This one, D is greater than P when shifting from non-polar to polar solvent. So this is the effect of solvent polarity. Now there are some Woodward-Fisher rules, which are postulated by Woodward and Fisher for calculation of lambda max in conjugated diene and carbonyl compounds. For that we have to learn something, that is what is homoannular diene. Homoannular means when the diene is double bond, conjugated double bonds are in the same ring. Heteroannular diene means where the conjugated double bonds are in different rings. And exocyclic and endocyclic conjugated diene. Exocyclic means if a double bond is outside of the ring, and this is endocyclic. Here this double bond is exocyclic to that ring. Similarly, this double bond is exocyclic to this ring, and this double bond is exocyclic to this ring. Now Woodward and Fisher formulated some rules that for homoannular diene, heteroannular diene, they have some basic values, and along with that, if some exocyclic bond, double bond extending conjugation, then we have to add some more values. So now for conjugated diene and triene system, for the transition of pi star, if the solvent is ethanol in a polar solvent, if we see, then Woodward and Fisher postulated some values. So you have to remember this table, that for parent value for butadiene system or a cyclic conjugating system, the value is 217 micrometer. If it is a cyclic triene, then 245 micrometer. Homoannular conjugated diene, then 253 micrometer. Heteroannular conjugated diene, then 215 micrometer. So these are basic value. Now if the alkyl substituent or ring residue, so what is ring residue I will tell in the example. It will be 5 micrometer will be added along with this or this or this. Exocyclic double bond, 5 micrometer will be added. Double bond extending conjugation, 30 micrometer will be added. Oxochrome, if OR group is present, then 6 micrometer will be added. SR group is present, 30 micrometer will be added. Chlorine or bromine, then 5 micrometer will be added. Similarly, NR2 is there, then 60 micrometer will be added. This is the example. Suppose this is a diene system. So basic value is 217 micrometer. It is already written in the table. Now, two alkyl substituents. This is one alkyl substituent. This is one alkyl substituent. So 2 into 5, 10. Two ring residues. Suppose this double bond is here. These are also substituent, but it is in a part of ring. So 2 ring residue, that is 2 into 5, 10 micrometer. One exocyclic double bond. So the ring is bonded with a exocyclic double bond. So that is 5 micrometer. So the total value is 242 micrometer. Similarly, we have this example. Basic value 4 ring residue, 1, 2, 3, 4. This one basic value 3 ring residue. This one, and this one. Substituent with the double bond. That means, and one exocyclic double bond. This is the ring. This is exocyclic double bond. Similarly, this one. This is heteroannular diene. Basic value 3 ring residue. One is this one. One is this one. One is this one. Then one exocyclic double bond. This double bond is the exocyclic to this ring. So these are the examples. Similarly, for alpha beta unsaturated carbonyl compounds, we have some values: exocyclic double bond, allyl substituent, alpha position, beta position, gamma or delta position, then double bond extending conjugation, homoannular conjugated diene. Then if some groups are present in alpha position, beta position, gamma position, they all have different values. If we see the examples, this is one. Basic value is 215 because of this alpha beta unsaturated ketone. 2 beta ring residue. This is beta position. This is alpha beta 2 ring residue. 24. This 12 is already in the table. One exocyclic double bond. So this is 5 micrometer. This ring is double bonded exocyclic. The value is this one. Similarly, in this example, basic value 215, OH substitution at alpha position. This is alpha, OH substitution 35 micrometer. 2 beta substituent. One is this one is methyl group, one is ring residue. So 2 into 12, 24. Value is this one. So these are some examples. I am giving you some another examples. You just do practice and the answer and match with your finding with the answer. I am giving the answers also. So that's all for today. Thank you.